up above, and that region looks like that. Okay, so for C, you guys have it in front of you. Give me just 1 second here and I'll catch up. So I've got this line and then this curve right here. There's our region. So this will be really similar to the one that we finished with yesterday. So this will be a good review and just some good repetition, some slightly different situations. So C says, write but do not evaluate, kind of the same wording that we did before. An expression for the volume of the solid if R is rotated around, not the horizontal line y equals 5 like before, but the vertical line x equals 3. Negative 3, thank you. Yes, it was. So this vertical line x equals negative 3 is going to be over here somewhere. So I'll just draw that in and label it x equals negative 3. And then our region is going to be revolved around that. So, kind of like yesterday, do you see how there's going to be a pretty large hole in the middle of this shape? See if you can use some Play-Doh and make it, and we'll go back to the paper and see if we can calculate the volume of it. Of this solid. Let's think about what we're going to have to do detail-wise with the math. We're just going to set it up to where if we wanted to math 9 it or something, we could. Can we remind ourselves real quick? So Play-Doh should be out of hands. I know it's distracting, but Play-Doh should be out of hands. Pencil or pen in hand. Let's remind ourselves, or at least I need to remind myself, what is the equation of that line? Is it x over 2? Y equals x over 2?
Y equals x over 2.
Okay, so y equals x over 2, and the curve was that root x? Okay, so y equals root x for that. So let's remind ourselves about the relationship between the axis of symmetry, or the axis of rotation, and the representative rectangle. What's that relationship? Perpendicular. It's got to be perpendicular. This is a really key point, right? This is the jumping off point where if you don't know that, you're going to be using wrong variables potentially and mixing everything up. So what Delaney said is exactly right. We want a representative rectangle perpendicular to the axis of revolution. So what kind of a rectangle will this end up being? It'll be dy. It'll be dy. So horizontal will look like this. And so we name the rectangle for its thickness. Now the length is going to vary, right? If you think about it, down here at the bottom, isn't the length going to be really short? And up here at the top, the length will be really short again. But in the middle, the length will be longest, right? So the length is going to vary, but the thickness is measured on the y-axis, right? It's a vertical measurement to describe the thickness. So why that is so important is because if you have a dy rectangle, that means that everything in your integrand must be in terms of y. So really the big reason for doing the Play-Doh is so that you can easily, hopefully, easily recognize that this shape will have a big gap in the middle, in fact specifically a hole on this one, and so whenever you have that situation you've got to use the washer method as opposed to the disc method, which is a solid shape. So with the bless you, with the washer method, the way we set that up is we write volume equals pi integral big parentheses squared minus little parentheses squared, and we already decided that it's going to be dy. So let's fill in the limits of integration. Guys, get these details. I want you to be able to say this in your head right. The only way for you to say it in your head right is to hear it and then repeat it, maybe in your head or something. But if we're using a horizontal representative rectangle, what is the direction of accumulation? Is it bottom to top or left to right? Bottom to top. And so we're going to be accumulating from the bottom of this region all the way up to the top of that region. So what would be the lowest number of accumulation? 0. I agree with you there. So from y equals 0, bless you. And then what is the high value going to be? 2. You guys agree with 2? Yes. Okay. So 0 to, see here. When x is 1.
That was 4, 2, right?
Was that?
No, that was a different problem.
That was a different question. I don't think it's.
It should be 1 then.
Isn't that point out there 1, 1?
No, it's 4, 2. Oh, yeah, it should be 0 to 2 or 2.
4, 2? I don't have it in front of me, so I'm just asking. So 4, 2. So 0 to 2. Why don't we pick 0 to 4? Because x, yeah, 4 is in x, and that would be a left to right accumulation. We're doing bottom to top.
You're right.
So you will be forced to make a decision like that. Okay, so pi integral 0 to 2. Now we got to figure out the big radius and the little radius. And this is kind of where we finished last time. So what I'm going to do is draw that in, or attempt to. I'll just use a different color here. So this is going to be green. So from the axis of revolution over to, say, well, you know what? I don't really like that right there. Let's go here. So from the axis of revolution all the way over to there. Wouldn't that be the big radius? From the axis of revolution all the way over to the line, that'd be the big radius. So let's think about what this is. I know that this distance right here is going to be a 3. I'll kind of leave that on hold for the moment. But how far is it from the y-axis all the way over to that right edge? What would we call that? X. So if we were going to be consistent with what we did last time, was we did the axis of rotation minus whatever the distance was. And so you could say this if you wanted to. You could go -3 minus x. But of course, that's not going to work, right? Because we have a dy rectangle. Everything has to be in terms of y. And so what could I replace that x with that's in terms of y? 2y. So I'd erase the x and put 2y. And then with the other one, the small radius, I'll do that in a different color. I'll do questions here in a second. Small radius in purple. The small radius would be from here over to there. So that would just be -3 minus a different x. What would be the x with that? Y squared. So it would be -3 minus y squared. So again, I want to make sure we understand this. I'm giving you kind of a framework that will always work. To find your radius, if you simply take the axis of rotation minus whatever that x or y distance, whatever it happens to be, that will give you the full distance. I want you guys to think about something though. I really do. Mark, you okay?
Yeah, I'm okay.
I want to point something out. Nobody's really said anything, and you guys were kind of discussing. I didn't know if you were talking about what I'm about to talk about. If you think this through carefully, -3 minus 2y. Won't that, just that expression right there, won't that always be negative for this?
Yeah.
Aren't all the y's going to be positive over there? And for instance, y might be like 1/2 or 1, or all the way up there to 2 or something. All the y's would be positive, so it'd be 2 times a positive, so it'd be a negative minus something. That's going to be negative, isn't it? That might be a little disturbing because you're like, well, how could a radius be negative? Well, the truth of the matter is, if you wanted to do this a little, essentially backwards, if you wanted to do 2y minus -3, or y squared minus -3, you would get the exact same thing. Like if you flip the order on the subtraction, wouldn't it be fair to say that, wouldn't 2y minus -3 always be a positive? So why would my idea with the negative still work? Because it's being squared. So I want to just let you know, and I think WebAssign is somewhat flexible on this, and I obviously will be as well. If you had this or this in place of what was above, you'd get full credit. Simply because you're about to square it, and whether it turns out to be a -3 for a distance, -5, or a +3 or a +5, squaring it is going to turn whatever it was into a positive. And so I just want to let you know the standard that I usually take is I always go axis of revolution minus whatever distance is going on there. Because you're squaring it, it's always going to work. Always going to work. But just so you know, like the difference, when I say difference, I'm talking about this difference right there and right there. If you flip that around, it'll still work okay. The one difference you can't flip around is this one right here. Right? It needs to be big radius squared minus little radius squared. That order cannot be wrong or different than this. But within the little parentheses, that actually can be flipped around. So I just wanted to let you guys know that. I didn't know if that's what you were discussing or if there's anything yet to discuss with that. But at this point, I think I'm done unless you have questions with that one. Is there anything out there you want to ask? Okay, so then this is your chance to try this on your own. D, write but do not evaluate an expression if that same region is rotated around the horizontal line y equals -2. So this is your chance to try this on your own completely. See how it goes. We'll look at a solution in a couple of minutes. The answer to this one, volume equals, could you guys stop with the Play-Doh?
Yeah.
Thanks. Volume equals pi integral from 0 to 4, and it would be -2 minus root x squared minus -2 minus x over 2 squared dx. So that would be a complete answer as far as setting it up but not evaluating it. Do you have any questions? Now's your chance. We're going to leave this alone from here on out. Yeah?
Can you explain why on all these it's -2 minus square root of x?
Yeah. So we're talking about distance. So to find the distance between two objects that are at a certain position, we always subtract. So I'll give you an example. Let me just replicate this graph real quick. So we got this and we got this. And it was -2 down here. So to find the distance, so like if I say, you know, my big radius goes from here to here, what I would say to find the distance is this. Right here from the axis of rotation up there to the x-axis, that's like a distance of -2, correct? And then from here to here, that's a distance of y, right? I'll just put an arrow right there. The distance of y and a distance of -2. So to find the complete distance, you could think of it a couple different ways. You could just say, hey, one of the distances is 2, and the other one is y, so the distance complete would be 2 plus y, right? That'd be one way to think about it. Or you could say, like we did in this one, we could say the -2 minus y, where we see the subtraction coming into play. The reason why both of these work, they're the same number, right? Just one of them is positive, the other one's negative. And so to find, you could, like this is kind of the alternative method I just showed you a second ago. You could get into that if you wanted to. Or if you want to just be consistent and say, I'm always going to go axis of rotation minus whatever function or detail is in there, you could do it that way. But they both work. So for instance, like if the y happened to be, I don't know, say 3 right there, we can see clearly the distance is 5, right? So if I followed this line of thinking, I would get 2 plus 3. If I followed this line of thinking, I would get -2 minus 3. So one of them is 5, the other one is -5, and you think, well, those numbers are different. Of course they are, but you're about to square them. So the result ends up being the same thing. So the order really doesn't matter in there. So I'm flexible. Like I could take either one of those and be okay with it. Did I get your question answered? Okay. Anybody else? Big question, little question, detail, big concept, whatever. Let's try to get things cleared up if they need to be cleared up. Okay, fair enough. So we are going to do something a little bit different. So I'm going to ask you right now, this is going to require your full attention. If you're half Play-Dohing and half thinking, it's not going to go well. So take the Play-Doh, stuff it back in the bucket, put the lid on. We will get it back out in just a second. You're going to be challenged again to come up with a good shape. But for the moment, let it go. Let's see here. Do I want to do that? I don't want to do that yet. I want to do this. Okay. So if you keep going in your notes, flip over. This is the final top. You've finally gotten here. This is a good place to be. We'll try to get this finished up here somewhat quickly. So solids with a known cross section. So I want you to think a little bit about cross section. I'm going to show you a demonstration in a minute, but I want you to think real quickly about a cross section. A cross section is almost like a cutting with a knife type of a thought process. So can you picture an orange? If you take an orange and you take a knife and you cut the orange in half roughly, and you take the two halves and you look at the two halves, what do you see?
The 2 halves of an orange.
A circle, right? A circle. As close to a circle as nature would produce, right? Seriously, you get what I'm saying, right? So the cross section of an orange would be roughly a circle. Okay, now that's not always the case. Like think about a Snickers bar. You take a Snickers bar long ways, you set it on the table, you take a knife and you cut it, and you look at the ends of what you just cut. What does that look like? Also funny, yes. Rectangular-ish, right? Trapezoid-ish, rectangular-ish. I mean, I realize it's got a little bit of a wave to it, but it's definitely not a circle, is it? It's more of a rectangle, square, trapezoid-y kind of a thing. And so depending on the shape, when you cut it and look at the ends, it's going to be different shapes, and they're all cross-sections, right? They're all cross-cuts, if you will. And so what we're going to look at here finally is how you could create a solid with volume, not using revolution like we've been doing, but instead using an accumulation of cross-sections. So a little bit, it's not a rotation. We'll describe it, and I'll show you some demos here in a second, and I'll draw hopefully some good pictures. But it's a cross-section accumulation versus a rotation accumulation. Your question?
Can a cross-section, like instead of being vertical, also be horizontal? Like if you cut the Snickers bar?
Right, yeah, you could. You absolutely could do it. We'll think of it more of just coming down on top of it instead of slicing it parallel with it. It's more going to be a perpendicular cut for us. Yeah. Was that?
So we're just like taking a bunch of the y-axes, or like a bunch of the graphs, and then like putting them next to each other.
Not quite. So what you're going to find is that like these graphs that we've been looking at to create like region R or whatever region, that's actually going to become the base of a figure, and the cross sections are going to spring up from that, as opposed to something being rotated. I'll draw you a picture. I'll show you a demo too. So like as I've noted here in your note packet there, these solids are not caused by rotation, but a sliding or an accumulation of cross-section along a specific path. So I want to point something out. With all of our volumes by rotation, all of them involved pi, didn't they? And it's because of the rotation, right? Pi r squared is basically a circle, created, turning into a little disk and add it all up and all that stuff. So that's why pi was involved in all of those, because of the rotation. Now with these, pi won't be involved with all of them. It's possible it could be, but I'd say the vast majority of them, no pi's, because there's no rotation. So what I'm going to do is I'm going to attempt to draw this out for you. And I'm debating about whether I'm going to, I'll do this on the video. I'll see what I can do with this. Hopefully the art makes sense. So we are used to seeing the x-axis and the y-axis in a certain orientation. Wouldn't it be fair to say that we are used to seeing the x-axis and the y-axis kind of like this? There's the x, there's the y. And isn't it almost like like you're in an airplane looking straight down on the ground? Isn't it amazing? Like you look down on the ground from an airplane and you see all the roads and all the farmers' fields or whatever, if you're flying east. But all the roads are just like, you can clearly see that most of them are just like grids, right? North and south, east and west. This is kind of like that. It's like you're in an airplane looking down on the roads and see all the roads going east and west, north and south. But that's not really the case when your perspective changes, is it? So when you're flying in the airplane, you're way above the earth, you look straight down, you see the roads. As the airplane comes in for a landing, now all of a sudden you don't have the same perspective, right? So what I'm getting at is, if I stand up here, it's like I'm the airplane, right? I'm in the airplane, and I'm looking down and I see this crack in the tables. They've never broken. Hopefully they won't today. I see the cracks in the tables. That's almost like the roads, right? So I'm standing up above them, and to me it looks like a T, right? To me it looks a lot like a T from my perspective. But if I get down on the ground and I look at it from a totally different perspective, it does not look like a T anymore. If I get down here more on ground level, now it's like all of a sudden these weird angles appear, right? Now I know from having been up there, I know that they're not at angles, but my perspective tells me, okay, they seem like they're going at angles. The taller I get, the more I can see. Yes, you're very funny. The more I can see that they actually are right angles. So what I want to do is I want to compare this view of the x-axis and the y-axis with more of a ground level view. So instead of drawing it like this, I want to see if you can visualize this with me. I would say that the x-axis, I'm going to still draw horizontal like this. But I'm going to have the y-axis kind of go off into the distance. So this is x, this is y. Now they're still perpendicular to each other, but it's like I'm seeing them more from ground level, like a perspective drawing. You know what I'm talking about? You know how the train tracks? Think about it. With train tracks, if you get down and you look at the train tracks, you're standing right on the train tracks, there's no train coming, hopefully. Don't the train tracks appear to touch way out there? Do they touch though? Of course they don't, but your perspective tells you otherwise. It's a little confusing. You're like, hey, they seem to be going towards each other. This is a perspective drawing, like a three-dimensional look at the x-axis and the y-axis. I think I'm reaching some of you, but maybe not all of you. So here's another way of looking at it. Here's a grid, right? So if I look at this grid, you guys can help me, you guys are closest. If I look at this grid in one perspective, it looks a certain way. If I look at it like this, you look straight down on it, you see perpendicularity, right? But if I raise it up, effectively like lowering your elevation, the lines don't look perpendicular anymore, do they? There's some crazy angles a little bit, right? So that's the perspective I'm trying to reach here. Does that make sense? Sir?
So are the x and y axis both going to be on the same plane? And there's going to be
Yeah, they're on the same plane, exactly. They're on the exact same plane.
Z-axis too that goes up? Or?
We're not going to have a z-axis here, but if you were going to, let's talk about that. There is no z-axis. But if you were going to draw one, the z-axis, which would be your third dimension, would look like this.
Where's time?
Oops.
The fourth dimension.
Can you see the z-axis here? It's going straight up. We're not going to have that though. So don't feel like you need to think anything about that. So here's what we're going to do. Here's what this accumulation by cross-section really is. I'm going to draw in a region that we typically have. I mean, we've seen this sort of region a bunch. Some curvy thing and some other curvy thing. There's my region. It kind of just stretches out there into the first quadrant. So instead of, see if you can see this. Instead of what we were doing, where we were taking this and rotating this around an x-axis. That's what we used to do, right? That's what we've been doing. Do you see the rotation? Like this would be down here, and there would be another one up here, like that. My drawing gets a little bit messy here. We're not going to be doing that. No rotation here. Here's what we'll be doing. I'll show you a computer demo of this here in just a second. I might say my cross sections are squares, let's say. So my cross sections would actually spring up from this region. I'm just drawing in some selected representative cross sections. Do you see how they're like growing up out of that base region? So with this situation, your region R, which seems to be called a lot, is not going to be rotated around anything. It's just going to sit there, and almost like when you plant seeds in the ground, things spring up from the ground. It's almost like somebody is planting square cross sections that spring up out of the region. And if you have enough of them, you create this solid, and we can find its volume. So can I show you a little bit of a different demo here? Let me show you something a little bit different, one of those Wolfram Alpha things.
With the bigger one?
Nope, I want this. There we go. Okay, so Wolfram Alpha, like this. So yeah, I can grab this shape. Okay, so here's what this is talking about. What's this? Oh, okay. Anyway, so this gray circle over here is representing the base region. The base region. And so if I take this shape and flip it upside down, you see the base region, right? Okay, so then what's going on is these are, you can see up here, the base region is a circle and the cross sections are squares. So if you look really carefully here, do you see all the little black lines? I'm kind of tracing right here. Oh, you can't see it up there. All the little black lines, like right here, like that. Do you see how they're all square shapes? And it forms this region by just accumulating these square shapes that are like growing up out of the circle. No revolution happening here, they're just growing up out of the circle like a plant or a flower growing up out of the ground. We could change things, right? What if the cross sections were not squares anymore? What if they were equilateral triangles?
Look pretty cool.
Can you picture this? Circular base with equilateral triangles growing up out of the base. Show you what it looks like. Still circular base, you can see it, but it looks like kind of a mohawk. So you see how, when you compare, do you see how the bases are, or the cross sections are squares there, equilateral triangles there? See the triangles? Question?
What defines how large the rectangles are gonna be?
Well, so let's go back to the squares. So the squares have to stretch across the circular base. And so that means that as the squares, like as the little cross sections get out towards the end of the circle, the distance between the points of the circle will be really tiny, so they'd be short squares.
So you couldn't have like a completely known unless it was like equilateral triangles or squares.
Well, as long as all the shapes are similar, then one nit.
Like,
Well, so they'll all be,
It's a
yeah, they
square
are
circle.
similar shapes, right?
it's a square,
But
all
they
four
have to be
sides
like
have to be the
squares or
exact same.
equilateral.
Yeah,
So
like
each
you
one-
can,
Could they be?
like, cause if it's
They need to be
known
the
that
same
squares
shape
equilaterals, but if it's
uniformly
just a
throughout
rectangle,
for us. Or we
unless
could
the
do it
first
if they
one is
change, we just have to have
defined,
multiple
then you don't
intervals.
know how big it's
Um,
gonna be.
How does,
But I'm still kind of wrestling with the, what do you mean by similar?
So like they're the same shape but just different sizes.
Exactly, yeah, so like the squares, yeah, the squares on the end would be really tiny, but the squares in the middle. So the squares, like, to go back to the squares here, like looking down vertically at it, the squares would stretch across from there to there. So on the end, the squares would be pretty small, right? And so like this would also govern the height of the square too, wouldn't it? And then here in the middle,
Why is that gonna govern the height though?
because a square has, because specifically it's a square, the side length is all the same. Yeah, and it would do the same thing with the equilateral triangle, because with equilateral triangle, it's a triangle with all the side lengths being the same. But with rectangles, you could have some flexibility on that.
I was just about to ask, how would you determine the shape of rectangles? Because like even with the semicircles. you
So
don't
yeah,
know.
so if they wanted you to use rectangles, they're gonna have to say something about the height, right? It's gonna have to either just directly give you the height, or maybe give you a relationship between the base and the height, like,
Yeah.
I don't know, like the height is 3 times the base, or the height is always 10, or who knows, that could be some variation on that. Yeah,
And
go ahead, quick.
Like, doesn't the volume then change if you're using squares or?
Totally.
Okay.
Squares, triangles, whatever cross sections, the volume will change based on that.
So they'll tell us which one.
Oh yeah, definitely. The setup will say the cross sections are triangles, the cross sections are squares, blah, blah, blah. They'll give you the details you need. Yep, for sure. So there's the triangle one again, the cross sections are triangles. What if we leave the base circular, but then the cross sections are semicircles? Can you picture what that would look like?
like a less pointy little box.
A lot less pointy. Wouldn't it just look like half a sphere? So again, there's your base, right there. And can you see how the cross sections are now circles?
The bald head.
A totally bald head, yeah, there you go. And then finally to the rectangles. Hey guys, again, circular base, rectangular
Oh, yeah.
cross section. So it looks to me like with this one, maybe the height is like half the base length or something. It didn't really specifically say what relationship they used there, but something like that, yeah. Question?
And so you're not, I'm assuming you can't do cross sections with more than 4 sides, because then it'll make it not a function, because it'll go over itself.
No, you could.
So
You
like
could
if
do
you
cross
wanna do
sections
like
with,
an octagon,
Equilateral octagon, or like regular octagons or something.
Do you have a?
You
do
could-
what would that look like?
Well, so what would that look like? So like if you had a circular base, so here you go, circular base looks something like that in perspective, right? So if you had an octagon cross section, it would be a bunch of those.
Oh, gosh.
You could totally do it. So what you would need to know, the only extra information you'd need to know here is you'd need to know the area formula for a regular octagon. Do you know it?
No.
Not that that's going to be important in our class because we're not going to go there.
I know.
It's 1/2
I know.
times the apothum
I know what that is.
Oh,
times the perimeter. So it's 1/2 times A times B. That's not a formula you need to know. I've never seen anything resembling that on an AP test or my test, but it's still an interesting question. You could definitely do it. Hang on a second. Go.
Are those colors just to make it look pretty, or do they mean?
Yeah, just to make it look pretty. So yeah, I think you can see the different sides and kind of distinguish between the top and the sides and the bottom.
weird shape.
And pretty it does look.
You know, doing it with hot guys.
Go ahead, Jonathan.
Could you do it with concave angles? Like if you want to do a star shape, would it be able to circle go in?
The key, the answer is probably yes, but the key is knowing how to write a general formula for the area of whatever that cross section was. But yeah, I'm sure you could. It's just a question of how you set up that area.
Is there an equation for that? The general area of the star?
Probably. Depends on how many points it has, I guess. I mean, I'm sure we could come
Star
up
of
with it.
David.
Because it's basically just triangles with some other polygon in the middle.
That's the AP test for the Christian kids.
So,
Cross section with the Star of David.
I don't know if you're a Christian or not, but I don't think you understand the Christian faith if that's what you think.
Isn't Jews?
If you think that's the meaning of it, then I don't know what to tell you.
Or-
So what if we have a,
Torah then.
so what if we change the base a lot? So like what if,
Hey.
oh, I don't know. What if we have a, check this out. What if we have, there's a triangular base right there with circular cross sections.
Yeah.
It can get very odd looking, yeah. There's pretty good representation.
It's like foot stack.
Looks like
Yeah.
that one robot in the robot movie.
Yeah. It gets interesting. What if the base, this would be more of an AP sort of a question. Like what if we had a base like that
Oh boy.
and square cross sections?
Yikes.
So you see how the base is basically, oh, listen, stop making those weird faces. You're like, what if the base is essentially created by two different functions, like that? You can see that it's a curve down here and a line up there, and the cross sections are squares. It's hard to visualize. The math is really not that hard to do.
Wait, can you do a top view then?
Top view.
Oh, that's so weird.
So, like, here's the base length. If we orient this kind of the same way,
Peculiar.
like there's a, I can't,
For some reason, it's like
There we go.
reflected.
yeah, it's rotated a little bit on me. So there's, you can see the base links, or the base regions kind of match up. Then you flip it over and you can see that you got square cross sections. So the whole point of this is simply to help you visualize what's going on. I think that it's very helpful, but the math aside from this, listen, you could be terrible at visualizing and still be very good at the math. I'd rather you be good at both. That's why we're taking the time to do this. So anyway, I just thought I'd show you some of those demos.
What is the last shape on the base region sign?
The what? The last one?
Yeah.
It's undulating, so it's like a sine or a cosine type deal. Yeah.
Oh.
So sines and cosines.
That's true.
You can see the base length in blue right there. There's the base, or the base region.
It's like one of those
Is
bases
that
that rich
equilateral
people have.
triangles?
Sure. Oh, the equilateral triangles looks cool. Looks like some kind of a temple. It reminds me of the Air Force Academy chapel a little bit, right? You guys ever seen that?
Yeah.
Kind of like that a little bit. Anyways, Jonathan.
So, does it ever go on both sides of like the z-axis where it goes both up and down?
You could. You just double it.
Okay.
We won't do that, but we certainly could accommodate for that.
Oh, that's cool. God bless.
Bless you.
Can you do
Okay.
this?
Why is
the
there a
semicircle?
hole in it?
Sure.
Looks like the base on Hoth from the.
It
The
does.
shield generator.
Yeah, the shield generator.
It's totally a Star Wars thing, isn't it?
Wow.
Right there.
That's how they made it. That's it. Right
Let's
there.
do some
Cross-section.
cross-sectional volume. Yeah, Star Wars. Must be it. Must be it. Okay.
That's so cool.
So let's see here. Let's get out of that if we can. There we go. Okay, so let's. This will work out okay. Let's turn back to this. Let me give you the details on how to find these, and we'll do one of them. And we'll obviously you can see we're not going to close this up today. You guys asked some really great questions, and so I'm fine with that. And we'll just kind of run with this for now. I want to give you the details on how to do this. These are really complicated looking at times, but the formula, thankfully, is not that complicated. So here we go. The formula's here. If the cross sections are perpendicular to the x-axis, we will be using dx thick cross sections. If the cross sections are perpendicular to the y-axis, we'll be using dy thick cross sections. But here's the formula. Volume is equal to the integral from a to b, with a and b just being with the limits of accumulation where you start and you stop. And then the integrand is going to be a of x dx, or if it's going to be in terms of y, it's going to be the integral from a to b of a of y dx. So I think I need to explain what a stands for, right? So it's either going to be, let's go with dy right there, my bad. Your frowny faces make a lot of sense in that case. Thanks for making those. The A, here's what it stands for. A in both cases, whether it's in terms of x or y, doesn't really matter. A stands for the area of a cross section. So it's going to be an area formula. So I'll give you some examples. If your cross sections are squares, what is the area of a square?
Base times height.
No, be more specific. That's a rectangle.
Base
Base
times
times
height.
base.
Base times base, also known as
Base squared.
base squared or side squared, depending on how you want to look at it. So if your cross sections were squares, you'd go with side squared. What if your cross sections were rectangles?
Base times height.
Base times height, length times width, however you want
So
to term it.
then, would the x or the y be the base?
No, the
No.
x is the function.
So,
Right.
so I'm saying a of x, in other words, like the area would be in terms of x. Or a of y, the area would be in
No, I
terms
mean
of
like the
y.
y, like for a of x, the y is the base?
No, it's
No.
a of y. So so if you think about this, like a, like the units on a would be like inches squared
Mhm.
because it's an area. So a of y would be like square inches, dy would be inches. So square inches times inches would be a volume, right? Cubic inches. And so a of y, you're talking about like the base length of a cross section. That's going to really depend on what is creating the region.
Mhm.
We'll get into the details of that in a second. But the reason why I said it is because, like with a circle, like if the cross section maybe was a half circle like that one we saw, then there's no base at all, right? It's a radius. So in a case like that, if the cross sections were circles, or I mean semicircles, it'd be pi r squared over 2. So you wouldn't be asking what's the base length. You'd be asking what's the radius. And so certain things like rectangles might have base lengths, squares, kind of the same thing. Even triangles, but circles or maybe other shapes, if we did like do the octagon thing, we wouldn't really be concerned about the base as much. So I'll show you, we'll do an example here. Yeah, we'll do at least one example before we go, and I'll show you kind of what I'm talking about. So those are the basic formulas. If you could do the area of a cross section, so it's going to require that you remember the area of a square is side squared, the area of a rectangle is base times height, semicircle, pi r squared over 2, rectangle 1/2 bh, right? So some of those really basic area formulas, you're expected that you would know that, just so you know. So can we do an example or two? Let's see how this goes. We are going to skip around somewhat. We're not going to do 5 first. Do I want to do that one? Yeah, let's do 6. Let's do number 6. So let's read it over. It says the volume of the solid formed with cross sections perpendicular to the y-axis that are squares. The circular base is formed by x squared plus y squared equals 9. Did you notice that there's nothing to indicate revolution here? There's no revolution at all, right? This is purely by cross section. So I'm going to sketch this out. We're going to try to make it with Play-Doh, create the shape with Play-Doh, and then we'll figure out what the volume would be. So I'm always going to draw these in perspective. One thing the AP test, one thing about that is they don't draw this in perspective. I think it's helpful here at the start to kind of see it in perspective, but just know that like on AP test you won't see it like this. You could always redraw it if you wanted to, but we're told that we have a circular base. So I'm going to graph this circular base. What's the radius on this circle?
3.
That's right. So with my circle drawn in perspective there, I would say over here is 3, over here is -3, down here would be -3, up there would be +3, just for perspective there. And then we're told that the cross sections are perpendicular to the y-axis. So I'm going to attempt to sketch one of those in here. And then I'll have you guys try to make this with the Play-Doh. Something like that. Do you see how it's kind of growing up out of the base? Does that perspective make sense? Okay. So, you actually saw something like this on that little Wolfram Alpha thing. See if you can make it with Play-Doh. I'm going to try to. This one's pretty tough. I think you're going to find this is fairly doable. Volume is equal to the integral from, let's talk about the integral first. Where would we start accumulating these cross sections?
From -3 to 3.
-3 to 3, right? We would start down here. We'd end up there. So you could go integral from -3 to 3. And the area of a cross section, they're squares. And so what I would do is this. Parentheses, squared. What's the thickness?
dx.
No, they're perpendicular to the y-axis.
Element dy.
So the length would be potentially an x thing, but the thickness is dy. Now here's how we finish. It's a square, and so the side length of a square is what goes inside there. It's side squared. So really what I'm asking you is, how long is this distance from this purple dot right there to that purple dot right there? How would you express it? It's going to be different depending on where you are, right? How would you express that distance?
3 minus x.
Not x, although x is really close. Say again?
3 minus y.
Not 3 minus y either.
It would be, so it would be y.
Not yet. Not yet. Let me help you with this. If I start on the y-axis, this is the y-axis right here. If I start on the y and I measured out to here, what do we call that distance? Not
X distance.
It's not 3 anything. It's simply an x, isn't it? Okay, well, so does this x right here, does that describe the entire side length? Isn't there another one on the other side?
Yeah.
So the full side length would be 2x. So 2x is your full side length, but we don't want that x there. What could I do to get rid of the x and have just a y?
Solve for y.
That's right. So if I solve for x. So if I solve for x, I get x equals root 9 minus y squared. So my final answer, at least as far as setup goes, would be integral from -3 to 3 of 2 root 9 minus y squared dy. So it's simply side squared in there. The issue is simply going to be with stuff like this, figuring out what the side length is. That's going to vary depending on what the base region happens to be. So, guys, I think all of Tuesday we will just finish this up. That'll leave us with 2 good review days leading into our quest on Friday. So, have a wonderful rest of your day and a good weekend. See you later. Just leave the Play-Dohs where they are, but please put them in the buckets.